Hello. This is basic statistics. We're looking at confidence intervals, chapter 7, confidence intervals. So you can read on the first page the objectives and the three properties of a good estimator, unbiased estimator, consistent estimator, and relatively efficient estimator. So those are the three things that make it a good estimator. Let's talk terminology. We're jumping down to C. So an interval estimate of a parameter is what we're measuring, what's being measured, is an interval or a range of values used to estimate the parameter. This estimate may or may not contain the value of the parameter being estimated. And so we could say you might get a confidence interval that looks like this. 82 is less than the mean, which is less than 88. So it's the interval from 82 to 88. And that's where our mean is. All right? A confidence interval is a specific interval estimate of a parameter, that's what's being measured again, determined by using data obtained from a sample and the specific confidence level of the estimate. So what that means, and this is a little confusing, that means I've got this red line is mu. It's the actual mean of the population. So let's say I have 90% confidence. A bunch of people kind of mess that up and go, oh, that means you're 90% sure, that means you're not really. What a 90% confidence interval means is if I repeated the process, let's say 10 times, let's say the first time I did it, I got that interval. The next time I did it, I got that interval. The next time I did it, I got that interval. The next time I did it, I got that interval. Next time, that interval. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, lovely. So look, this interval captured the mean, this interval captured the mean, this interval captured the mean. 9 of these, that 1, 2, 3, 4, 5, 6, 7, 8, 9 of these intervals actually captured the true mean, was within the interval. This one did not. So we have no guarantee, if we say it's a 90% confidence, we have no guarantee that this isn't the one that we just figured out. And so that's why you got to be careful when you say, oh, we're 90% sure. No, you're not. You're not 90% sure. That just means if I did this process many times, 9 out of 10 times, I would capture the mean. So it's likely it's one of these other intervals, but it's not impossible that it's that one. All right? Okay, so let's look at the next page, page 2. Confidence level of an interval estimate of a parameter is the probability that the interval estimate will contain the parameter. So the confidence level is the percentage equivalent to the decimal value of 1 minus alpha. That should read 1 minus alpha. So let's look at page 2 here. Number 3, the top of page 2 for the chapter 7 notes. That's what it should say is 1 minus alpha. I think it says 1 minus d or something like that. That wasn't supposed to be d, that was supposed to be an alpha. So if our alpha is 5%, then the confidence level would be 95. So look, what does that mean? If we have a standard normal curve, and it's a two-tailed test with an alpha of 5%, that means two-tailed means it's both on the top and the bottom. And 5% would mean that it's split. So this is 2.5% here. And this is 2.5% there. And that means we've got 95% in the middle. And so that's what we're talking about. If we say alpha on a two-tailed test is 5%, that means 2.5% on each one of the pieces of the tail. All right? So let's do an example, and hopefully this will make a little more sense. So the president of a large university wishes to estimate the average age of the students presently enrolled. From past studies, the standard deviation is 2 years. So they gave us the standard deviation of the population as 2 years. Remember, that's sigma, and whenever it's a Greek letter like that, that means it's for the population. All right, the standard deviation is 2 years. A sample of 50 students is selected, so that's our n. N is equal to 50. That's a pretty good size sample. And the mean is 23.2. Now the mean in the context of this problem is x bar. And so that's the mean of the sample. Whenever it's an x bar, that's a mean of a sample. If it was mu, then it would be the mean of a population. All right, so 23.2. Okay, so now find a 95% confidence interval of the population mean. All right, so we're actually going to look this up. And when you look that up on your sheet for confidence intervals, you're going to find this rather involved equation. And so don't freak out. It's a pretty large. It looks like it's a little intimidating. Don't be intimidated. It's only got 3 variables in here. And we're just going to substitute those 3 variables in. Now, this part of it right here or right here, the z sub alpha over 2, that's just a z-score that you're looking for. Don't worry about the little alpha over 2 part. All right, we're going to look up a z-score, and I'll show you on the chart. Okay, so let's take a look then. Now they gave us x bar. That's 23.2, so we can put in 23.2 right there. Minus this alpha, we have to look up for 95%. So 95% confidence is what they wanted. And so we need a number for a z-score that goes with 95% confidence. And so here's what we're going to do. We're going to grab this chart, and I'll show you how to use it. So first, on your formula sheet that you get to use under Chapter 7, let's see, where's Chapter 7? There's Chapter 7. So look, this is the one that we want. That's the one that I just put on the board. And I don't want you to really worry about that alpha over 2. Just think of that as a z-score, okay? So now, if you flip a couple of pages to table F. So table F on 95%. And follow it down to 9. Okay, so 0.96. Okay, so what we do here is you just look on table F. So go to table F there. And on the very top, it says for confidence intervals, There's 80%, there's 90%, there's 95%, there's 98%, and there's 99%. And so when we're finding, don't worry about degrees of freedom yet. I'll show you that in the future. Right now, all you have to do is find 95%, that's this, and then follow it all the way down to the bottom for the z-score. Look, oopsie, that was my bad hand, sorry. Let me get that. I put a little star by it, the z. So the z-score for 95% is 1.960. 1.960. All right, so that's table F, confidence interval, 95%. So that our z-score that goes with 95% is 1.960. So now what we do is we sub in for z, alpha over 2, 1.960. They gave us that as 2. They gave us that as 50. This is still 23.2. And now this is going to be exactly the same as that. So what I suggest is let's do this calculation. This 1.96 times 2 divided by the square root of 50 is this value, 0.5544. That's also referred to as the margin of error. This thing right here, what you're adding and subtracting from the mean on either end of the interval, is called the margin of error. So if you're a Three Stooges fan, hey Mo, margin of error. All right. And so we know if you put this into the calculator, it's going to kick out 0.5544. So we already know that's what's going on here. It's going to be the same, 0.5544. And now 23.2 minus the 0.5544 and 23.2 plus the 0.544. And our 95% confidence interval for this would be 22.6456 less than mu. That's the population mean. So we're doing an estimate for the population mean. And on the top end then 23.7544. And so now let's round it to tenths place. So 22.6 to 23.8 is our 95% confidence interval. Now, what does that mean if I were to interpret that 95% confidence interval? That means if I redid this experiment, I redid this process 100 times, 95 of the 100 intervals would actually capture the true population mean. There's no guarantee that this isn't one of the 5 stinkers that didn't capture it, okay? It's likely, it's more likely that it is one that did capture, because 95 out of 100 of these intervals would actually contain the true mean. All right? Okay, let's look at 7.2. And so when we look at 7.2, confidence intervals with t distributions. And so now the t distributions came about. It's commonly referred to as the student distribution. A brewmaster actually figured out the t distribution. What that does is it takes into account that if your numbers are small, if we look at what a t distribution, it's still bell-shaped, it's still symmetric about the mean, median, and mode are all in the same place. The curve never touched the x-axis. So those are all the exact same attributes as a z distribution, z-score. But here's the deal. Variance is greater than 1. Degrees of freedom are always n minus 1. So we're going to look at degrees of freedom as n minus 1. And basically, the smaller the size of the sample, the flatter the curve is. So the lower the sample size, the flatter the curve. And we've been hearing a lot about that. Flattening the curve is what they're trying to do with the isolation that we're going through right now. All right. So let's take a look at 7.2 example. So this is on page 4 of your note packet. It's the second example. 10 randomly selected cars were stopped and the tread depth was measured. The mean was 0.32 inches and the standard deviation was 0.08 inches. Find 95% confidence interval of the mean depth. Assume that the variable is approximately normally distributed. So let's identify the stuff that they gave us. First of all, n equals 10. That isn't a very large sample size. 10 is a pretty small sample size. They gave us the mean of that sample. But here's a key difference between this one and the one that we did previous. We don't have a standard deviation of the population. We only have the standard deviation of our sample. And so when you're given a small n and the standard deviation of the sample, not the standard deviation of the population, notice that's not a sigma, that's just an s, then we're going to have to use the t distribution. Now when we look at that, it's exactly the same. If you look at the formula on your formula sheet, everything is precisely the same as the one we just used. There are just two tiny little differences. T is substituted in for Z, so we're going to use a T score, not a Z score. And S is there instead of sigma, because we don't have the standard deviation of the population. We still call it the margin of error, and we're still going to do it almost exactly the same way that we did it before. The 0.32 is going to go here and here. We're going to find this margin of error. That's still margin of error. But T is looked up a slight bit differently. So a 95% confidence they want again. But this time we're going to use the T distribution. It's on the same page as where we found the Z confidence intervals. It's just that now we're going to follow it down, and here's a new added little wrinkle. Degrees of freedom. That's always one less than how many things you have. So 10 minus 1. So whatever n is, you take away 1, and so that's 9 degrees of freedom. So let me show you how to look that up on your chart here. So we're still on table F on the chart. All right? And we still want confidence interval 95. But what we're going to do differently now is instead of going all the way down to the bottom and say 1.960, we're not going to get to do that. We're going to only get to go, you look at degrees of freedom, df, and don't go to 10, we go to 9. We go to 9 because 9 is 1 minus 10 minus 1. So that's how we got the 9 degrees of freedom. When there's one variable, you do minus 1, and that's what we're going to be working with. So now follow that over to 95% and 9. And let's see, what is that? Is 2.262. So look at what that's different. 2.262. That's what's going in for T. And don't worry about the alpha over 2. All right, we already have the 0.32 for X bar. We got that for T, our T value. S was given as 0.08. N was given as 10. And now this is exactly the same as this. This is the exact same calculation. So let's just calculate it once. Let's put this in our calculator, 2.262 times 0.08 divided by the square root of 10, and then hit enter, and that should kick out 0.0572. So that's our margin of error, 0.0572. And so we take 0.32 minus that, and we take 0.32 plus that, and that gives us our confidence interval. So this is 0.2628, which is less than mu, which is less than 0.3772. And so if we round to hundredths place here, our 95% confidence interval would be 0.26 to 0.38 for the amount of tread left, the average amount of tread left on a tire. Now remember what 95% confidence interval means. That means if I redid this experiment, I did it another 100 times, 100 more times, I stopped cars, 10 cars, and measured the tread and found the standard deviation, found the mean and standard deviation of each one. That means out of those intervals lined up, if I lined them all up, all 100 of them, 95 of the 100 would actually capture the true mean of the population, and 5 of them would not. And so there's no guarantee whether this is one of the 95 or one of the 5. All right, it's more likely one of the 95 that actually captured it, but there is a possibility it's one of the 5. All right. Okay. Next video I'll do is for 7.3 and 7.4. So